Okay, waiting for a few seconds. Uh, can you hear me? Is the sound good? And can you see my slides? Okay, okay. Yeah, then I guess we can start. Yeah, so yeah, welcome everyone, and welcome to our webinar where we will be discussing how can we use fuzz testing to detect out-of-bound memory access or buffer overflows. And yeah, my name is Khaled. I am one of the co-founders from of Code Intelligence. And yeah, the nice picture you see here in on the slide is taken from our offices in Bonn. So we are located in Bonn. Yeah, so as I mentioned, so the goal of today's webinar is to discuss out-of-bound memory bugs or out-of-bound access bugs. What are these bugs? What do they mean? And what are the security implications of those bugs? And yeah, introduce a little bit or at a high level, so what fuzz testing is or what Whitebox fuzz testing is, and then see how we can use fuzz testing to automatically find out of memory or out of bound access bugs in our code. And then towards the end, I'll discuss some of the challenges adopting fuzz testing in a real in production or in teams, and then yeah, end up with some Q&A. And yeah, so I will be also monitoring the chat here. So if there's any questions in the middle or any things needs clarification, just feel free to write at any point in time, and we'll try my best to address them in a timely manner. Okay, dokie. So I think most of us have seen or so over the last few weeks similar pictures where we have sort of the dreadful blue screen of death of Windows, and yeah, this as you all know was caused by cause a global outage over in airports, train stations, shops, government, hospitals, and so this was a massive incident that was caused by a single bug or a single out of bound memory access bug. And yeah, so the maybe the only good thing about such incidents is that it sort of shows the criticality of such software bugs and sort of raise awareness that there is should be we should do something about them. And obviously, so this is not a one-time event or it wasn't one-time incident. So we've seen several similar high-profile incidents in the past. And if you remember, like a few years ago, we had also the Heartbleed vulnerability, which is also a read buffer overflow that affected one of the most popular and used cryptographic libraries, OpenSSL, which is the library that we rely on for secure and private communication over the internet when we browse the web, read our email or our VPNs, for example. So this was a very severe vulnerability that enabled attackers to steal sensitive information such keys or passwords and stuff like that. So this is not a single so the CrowdStrike incident was not a single event, but it's sort of it happens from time to time. And if we take a look at the higher of the bigger picture, we still see that that memory corruption bugs, which is basically the overall category or the higher level category of out-of-bound memory access, still one of the most relevant and severe types of bugs that can happen. So they represent almost half of the top 10 critical bugs in 2023, so last year. So this shows that these bugs are still very, very relevant and can have also critical consequences. But maybe just if we take one step back. So what are these bugs? And we'll show them. So maybe what they can do with a very small example. So an out of memory bug is basically an error or a bug that can happen when your program tries to either read from or write to a memory area that's located outside the allocated buffer. So usually when you want to store data or like strings or something like that in your program, you just allocate a buffer of a certain size. And if you try to accidentally read or write from outside this buffer, this would cause an out-of-bound memory access bug. And these bugs, they don't necessarily crash the program, but they can have also other severe implications. And the reason they happen for certain programming languages like C and C++ is that these languages are sort of memory unsafe, meaning that the responsibility of properly managing your memory mainly lies or mainly is the responsibility of the developer. And as we probably know, these bugs can have severe security implications. Like they can cause a denial of service by just crashing your program, as what happened with the CrowdStrike incident, or they can cause leakage of or exposure of sensitive data, as what happened with the Heartbleed vulnerability, or they can lead to enabling an attacker to execute or control the code that you execute. And also they have, of course, further severe implications. And just to make this more tangible, we can have a look at, let's have a look at this very simple program. So I have a very unsecure program to just check the password. So these two passwords, this is a C program. So all that I'm doing here is I have the correct password stored in a certain array or a certain buffer. And I have another one that actually where I allow the user to enter his or her password through this function. This function just takes the input from the user and store it in this buffer. And just for demonstration purposes, this is what we see. So we print both of them, and then we check if these match. And if they match, we say access granted. If they don't match, we say okay, access denied. And if I now compile this this program and try to execute it, so the first thing, say welcome to the secure server, please enter your password. So if I enter something like test, as expected, we should get access denied. And yeah, we see that this is the one that I entered, and this is the correct password. And also the expected behavior, if I had something like secret, yeah, I get access granted because these two matches. But if we look here, we see that this buffer has only 7 characters. So what would happen if I enter more than 7 characters? So if I now try to write test 1, 2, 3, 4, 5, I see something very interesting. which is now even in my code here, I don't touch the correct password or the buffer containing the correct password. Now you see that some characters that I enter just end up here. And this is exactly what happens here, because the language doesn't give me any guarantee about about the boundaries. So if I write more than I am allowed to, these few extra bytes will end up in the next buffer, which in this case happens to be this one. So what this enables me as an attacker, let's say, to do is, because I know the first 6 characters will match. So if I say try to enter something like hacker, and I know that the 8th character here or the 9th one gets into the second buffer. So if I run the same string again, now even though I entered the wrong password, in a sense, I was able to exploit this bug, and so that to trick the system to grant me some access. So this is obviously bad, shouldn't happen, but the memory unsafety of the language makes it possible. So I hope that this example illustrates what so one of the consequences that a buffer overflow can have. But then another question: what can I do, or what should I do in order to effectively find these bugs in my software? Because obviously, even if I'm as a developer, I didn't intend to write here. There was some scenario where user input ended up here. So we needed ideally a reliable way to effectively find these bugs, and by that I mean just first check or prove that this bug actually happened. So check a bug, so I detected the bug happened, and the second thing we need to provide an exact test case or a concrete input actually triggered this bug, because this way I have a very concrete example of what happened, and I can analyze it. And so the good thing about this is that these memory detection capabilities, you already have them sort of for free with any modern compiler like like GCC, for example, or Clang. And all in this case I have to do, I say I want to activate this, and what this what we call sanitizer, and what this would mean is when combining the code, this sanity checks or this runtime checks will be instrumented into the code, so that if I try to write over or read more than I need to, or I'm allowed to, this will just crash my application. So now if I try this version, if I enter like within the boundary of this buffer, it behaves normally. But now if I try our previous example with test 1, 2, 3, 4, I get something like this. So I get a crash from the bug detection capability that I instrumented into my code, and I get what's went wrong. This is stack buffer overflow, and here you have sort of basically the exact location where what went wrong. This is already a very good start. But what I needed to do in order to actually trigger this bug, I needed to somehow come up with meaningful inputs or good inputs that actually could actually trigger this bug. And ideally, we need an automated way where, because obviously these bugs, they don't just, so they almost always happen with jump corner cases that I, as a developer, didn't maybe think about. And so we need a way to automatically generate these test cases. And this is actually where fuzz testing plays a very important role. So, or what we mean also by Whitebox fuzz testing is where you have the source code, and then you can leverage the source code information or insight into into an effective method. So what currently fuzz testing or Whitebox fuzz testing is the most effective method to find bugs and security vulnerabilities in software. And so big companies like Google, for example, or Microsoft, find lots of their bugs with fuzz testing. So, but yeah, so what's this fuzz testing? The second component that enables us to automatically generate these test cases. So at a high level, the high level idea it's actually very simple. So I have a software under test. So this is my software that I want to test, and I have a fuzzer, what I call a fuzzer, and this fuzzer just simply generates some inputs, and hopefully by some of the inputs that it generates would then trigger some crash in my system, and this way the fuzzer then was able to generate an exact test case or an exact input that actually crashes my application. And this is exactly how fuzz testing started, like over 30 years ago. And this is still the main high level idea. But if we do this in a completely black box manner, it's very highly unlikely that we will not reach good code coverage. Because as we talked about, in order to actually have effective testing setup, we need to be able to create a test case or an input that actually triggers the vulnerability. So we need to generate test case that actually exercise or execute as much of the code as possible. And this is where the idea of let's take this insight from the source code and collect code coverage information so that we know exactly what we tested. And this is why one of the major breakthrough of fuzz testing, why it's so effective. So instead of considering it or considering the software under test as a black box, we instrument this code base. So while we compile the code, we inject certain markers, and these markers gives us feedback about for each test case or each input that we generated, we get a test case or we get a feedback. Okay, with this input, you are able to reach these code blocks. You were able to do this kind of comparisons, and all these signals that we get from the software, it's basically then used by the fuzzer to smartly or to intelligently do mutations or changes so that step by step we learn what input should we generate. And then if we take our image bars as an example, so if the fuzzer, we would start then with zero knowledge. We don't have any information about what are we testing. And from the instrumentation, we get something like this. So what we see here is green. As green are sort of the lines of code that were covered by this input. So as you see here, so the system or the software tries to compare this input by against some magic bytes, and obviously in this case all of them fails. So we get an unknown image format. But one of the signals that we get also is that my input was compared against these constants. So for example, FFD8. And so this is one of the smart mutations that the fuzzer would do, is that, okay, let's take this as the next input. What would happen? And if we do this, and now we see that we have a new line, a new green line of code. So basically, this comparison is valid, and in a sense, the fuzzer convinced the system under test or the application to treat this input as a JPEG image, and so we get to generate sort of valid images and do further mutations to that step by step learn or read more code. And yeah, the fuzzer doesn't get bored. Basically, it can generate hundreds of thousands of inputs per second, each time learning a new piece of information about the software we were testing. So this is what fuzz testing at a high level. And so you can visually picture it as if this is the software that we're testing is a software box or a maze. This instrumentation gives us exact information about which paths did we take. So what have we seen already? And so we know what we have tested and what we have not yet have tested. And this is so we have a good visibility into the software that we are actually testing. And from a sort of a developer mindset of the workflow, if we compare this to or fuzz testing to normal unit tests. So with unit tests, usually I have an API, my API that I want to test, and I come as a developer with some, or as an expert with some concrete input. So if I execute my API with this input, I get this output, for example. But I only test few test cases. With fuzz tests, we can picture it in a different manner. So we can picture that the fuzz test or the fuzzer will actually continuously call my API each time based on the instrumentation, based on the feedback that it gets from the system under test. It will try a smart mutation to get with an input that hopefully reach new code. And this is the feedback where it step by step learns about the application that is tested. And just to give it more, because we'll have a look at some of the examples, the more tangible. For C++, so Google Test is one of the most popular testing framework. So usually you would write a test as test, and then basically call your API or the function that you want to test inside this test. With the fuzz test, it should look very similar, but instead of test, you have fuzz test, and it takes two parameters. It takes a data buffer and a size, and this data is then generated by the fuzzer in each iteration. And then you can take this data, call your function with it, or just consume data from it, call the function, and then this is fuzz test will be continuously called by the fuzzer. And just also to have an example of how this would look like, we can have a look at this example. So what I have here is a function called explore me, and this function takes two integers and a string. And here we do some checks. So the integers need to be in this range. The string needs to actually to be a tagger. And if all these conditions or checks are met, we, in a sense, deliberately trigger a buffer overflow, a global buffer overflow. And so here we need these two components to be able to find this bug effectively. We need some way, a fuzzer that can generate inputs that actually satisfy all these steps, and bug detection capability that actually tells us, okay, here something went wrong. And yeah, and obviously something like this, to do something like it in a black box manner, it's very highly unlikely that by chance we generate a string that's attacker. And it's also where we see there's a limitation. For example, if you want to use other techniques like static analysis, where the static analysis would not be able to prove that that you can actually reach this function with this inputs. So it needs to do some approximation, would lead eventually to false positives in the results. And now in this case, if I want to test this function, all I need to do is write a fuzz test like this. So as we've seen on the slide, a fuzz test. You need to write a fuzz test that takes these parameters, and here are just some helper functions or helper data structure to get in some input of certain types from the fuzz generated data. And now I just call the function with these inputs. And obviously you can, there are, what I forgot to mention, there are some open source fuzzers that you can use, like AFL++ or libfuzzer. In this example, we'll use libfuzzer. And what you need to do is that you need to compile this function with the correct flags. So what I will show here, I will show this one with our CLI tool, which basically alleviates this work to automatically set the flags. And now I want to, so this is the function. and I can say, okay, this is the symbol checks fastest. I want to run it basically. And so if I run this fastest right now, it took less than a second or a second to trigger this bug. And what we see here, we see that it tells me there's a global buffer overflow in the trigger global buffer overflow function, and it gives me the exact location where this happened. So I can click on it, for example. I see it's exactly this copy was the faulty line of code. And with this example, I just want to mention that these kind of checks, which are almost impossible or very hard for a black box dynamic analysis to crack, they are very, very easy for white box fuzzers. So, and this is what we see here in this case. And yeah, so this is a very simple example of how to write the fastest and how fast it is to trigger the bug. But obviously, we mentioned previously Heartbleed, which is one of the most critical bugs that's caused by an out of bound memory access bug. And in this example, so well, it's nice to see that that fastest thing worked with a small example. Let's have a look. How can it handle such vulnerabilities like Heartbleed? And here are some interesting facts about this bug. So Heartbleed, this vulnerability stayed undetected in the OpenSSL library for over 2 years. So in late 2011, it was introduced into the code base. March 2014, it was discovered through code audit. So it took a year, 3 months or 4 months for this bug to be detected. But later, it was shown that if you use AFL, and this was 9 years ago, and AFL had just made a tremendous progress since then. So with AFL, you could have found this bug in 6 hours. But even more impressive, Kostya, which is who is one of the main maintainers of or developers of LibFuzzer, showed that you can actually find this bug in almost 10 seconds with LibFuzzer. And so let's see if this is true. And if you go back to this example here, I have the version of OpenSSL that's so this was the version that has the Heartbleed vulnerability. So if we have a look at this code, so this is actually the fastest that would test its functionality. So you do some initialization there, and at some point you call so you set the functionality data here, and then you call the SSL do handshake function. And here I'm starting from the fuzzer would start without any knowledge about about the expected messages. So now if I say ci fuzz run handshake fastest, which basically runs this fastest, you see the code will be built. Now the fuzzer starts to generate inputs that sort of try to maximize the code coverage. And as you see here, in less than 5 seconds, we were able to trigger a bug, trigger a heap of overflow in a function that's called TLS1 process heartbeat. And so this is where the name Heartbleed of the vulnerability came from. And you can go directly into this memcopy. So this kind of code, this memcopy here caused millions of servers to be affected by this bug, and it's called also massive losses basically. And what this means that if back then OpenSSL, which is now continuously fuzzed, had this fuzz test, it would take and the automation few seconds, 5 seconds or 10 seconds, just to find this bug after it has been introduced into the code base. So we would have saved a lot of effort and of unnecessary damage. And so this shows how, or a very prominent example of how fast, or why you should actually use fast testing. And if you go back to the CrowdStrike incident, so one of the this is a statement from CrowdStrike, and one of the technologies that they will now adopt in order to prevent or try to prevent these kind of outages of incidents from happening again is also fast testing. So this with these examples, I hope I was able to show how effective fast testing actually is, and that it's a good idea to use it. But there is no free lunch basically. There is if fast testing is so effective and is so good, why is not everyone using it or adopting it? And here, just want to take let's take a step back and discuss based on our experience with users and with customers. So what are the main challenges that's still remaining for this wide adoption of fast testing, and what you can do in order to solve them, and also show what we are doing in order to solve this. Well, there are what we've seen and what you currently can do very well with fully open source technologies, because these packaging capabilities are there. The open source fuzzers, libfuzz, are there and available open source. Everyone can use them. This addresses this step. So this where we can test or run the test, execute and optimize the test just to improve or maximize code coverage. But in order to do so, you need to already have fuzz tests, and this is basically the code that you need to write, similar to unit tests, but just taking the fuzz generated input and then feed it to your application. And imagine you have a very large code base containing thousands of lines of code, hundreds of functions. This becomes very challenging very quickly. And so for some teams or for some companies, the return of investment wouldn't match, because it's high reward, but it's high effort as well. And not everyone has the sort of the experience or the time or the resources to do so. And so I would like to show two problems or two challenges and see what you can do, and also show what we do to address those. Well, the first step is, as we talked, imagine you have a large code base, thousands of functions, or thousands of functions. So the question would be, okay, but where should I start? Well, should I write a fuzz test for each function, or should I write a fuzz test for a selected number of functions? And this becomes, especially if you don't have a very detailed domain knowledge, this can be challenging. And the next step is, okay, even if I know where should I start, I need to be able to write a high quality fuzz test, meaning a fuzz test that actually realistic in a sense that it actually calls the API or the function in a meaningful manner. Otherwise, we would have false positive in a sense that because we don't actually call the function they expect to have. And so these are the two main blockers that we see with users or with customers trying to adopt or want to adopt the fuzz test, but they see the value that they get from it. And so here I just want to show what we did or what you can do to automate these steps. So what we see here is a library which is called libyaml, which is a C library for parsing and emitting YAML files. And imagine, as I mentioned, this is a small library which is good for demo. For the demo, it's an open source real world project. And imagine you want to start. So either you don't know this library very well, or you don't have a full domain knowledge about it. So the first step, as we talked about, is where should I start? So, and usually this is a manual process. You need to either you know the code base very well, or you need to do some manual analysis, go through documentation, go through the code to see what's what's the best functions. Or what we find to be very effective is we can leverage static analysis there. That's what we do with CI Fuzz, is that we can, if we now ask CI Fuzz, let's show it in action first. We ask CI Fuzz to what we call candidates, which mean what are the best functions or the best entry points that I should focus on based on the highest impact that I can get. So what you do is, as you see, this is a library. It contains, I think, 6,000 line of code roughly. So the parsing this code is very, very, very fast. And what you can do is you can also automatically scan through this code base, parse the code, see which functions call each other, and based on this view, compute some metrics. So in this example, you see there are 59 functions that you can, potential candidates that you can write fuzz tests for. But so what we do is that here in this case, we leverage the static analysis to see for which functions, okay, how many lines of code I can reach. What is this? Because here, if you start with functions that can reach a lot of code, you get high code coverage with few tests, or the cyclomatic complexity. Like the complexity of the code is, the higher the probability is that you find something. There are some bug hiding around somewhere. And if you call any dangerous expressions or dangerous functions, as you see, this is this memory handling functionality, which actually can lead to buffer overflows. So basically, we bake all these metrics in a score that represents how important it is to actually write the fastest this function. So this is what we, based on that, it gives you hints into where you should start basically. And yes, this is the first step that you need to do. As we talked about, the next step is, okay, now I know which functions should I write fuzz tests for. And the next question would be, okay, I need to generate these tests. I need to create these tests. And this is the second step where we can also automate. And this is the idea here is that you can use is to combine both static code analysis to gain relevant context about the code base, and also the code analysis and generation capabilities of LLMs. So by combining these two informations, you can automatically generate fuzz tests. And this is what we also did with CI Fuzz. So if I now say let's say I want to generate a fuzz test for this top candidate, so I can say CI Fuzz create and give it the function. So what we do here, or what you can also do here is you can leverage static analysis to scan the code base, look for examples or where this function is used. Ideally, you have some unit test somewhere that actually calls this function. And this is a sort of a complete test case that's very, very helpful for the LLM to generalize into a good fuzz test. And of course, you need to tell it what a fuzz test is and how it should generate it. And in this case, if I now do this with CI Fuzz create, you would see, well, you see now some code is being generated here. And yeah, so basically this is a complete fuzz test that actually calls this API that I'm interested in. And so this one important thing is that as we talked about, in order to have a high quality fuzz test, if the fuzz test of this is the function, for example, you might need to do some proper initialization first, or some cleanup after you call this function. That meaning you need to call this function in a in a manner that respects the API contract. And this is information is already available in unit tests. So you can leverage this with the unit tests to generate high quality fuzz tests. And this is basically two things that you can do and that we actually did in CI Fuzz to try to automate these two steps, which basically, based on experience, are the main hurdles or barriers to entry for adopting fuzz testing. And so now I'm almost come to the end of the webinar. So the main takeaway from today's webinar that I would like to everyone to keep in mind is, first, as we've seen with the recent incidents, out-of-bound memory access bugs are actually very, very critical. They can have very severe consequences, and they are relevant. They sort of constitute majority of the or a big portion of the most critical bugs, and that white box fuzz testing is very effective in automatically finding these bugs. And as we discussed, there are challenges for wide adoption, but these challenges can be addressed and automated into to a great extent. And so this is what we currently focus on as a company, and what we do in our products is to make this as accessible as possible, as automated as possible for users. And obviously, as we've seen with the Heartbleed, so what we want to achieve here is that we don't release any bugs that fuzz testing could have found before, so that we don't have this major breaches. And with that, I come to the conclusion, the end of my talk. So thanks a lot for the attention. So I'll be available also in Twitter, LinkedIn, this email. So feel free to reach out. So also speaking of so what we discussed, some general challenges of fuzz testing. There are more specific ones related to some use cases or industries. And so automotive is one major area that we focus on. And if this is interesting for you, so on October, the 22nd of October, we'll have another webinar where we discuss how to enable completely software in the loop testing of automotive auto software, or more specifically auto cell applications at the system level. Yeah, and this is basically it. And let's have a look if we have any questions. According to you, what are the challenges, bottlenecks to adopting fuzzing, and how do you overcome them? So basically, what we discussed is that the main challenge is being able to create and write high quality fuzz tests. And this is where we leverage both static analysis and large language models to do that. And regarding maybe some specific use cases like automotive, there you have different challenges. That this is usually the software itself is meant to run on a special target hardware. And what we do here with our AutoSAR simulator, for example, is make it possible to run this completely on a Linux x86 machine, for example, which is easier to scale and to manage. Is this transferable to garbage collected languages? Yes, there are, for example, so we built the best sort of the Jazzer, which is a fuzzer for Java. There is also a second one for Jazzer.js for JavaScript or for Go, and there are, so you wouldn't find memory corruption bugs in the same sense that you would do for C++, but there are other types of bugs that you can have special bug detectors for. For example, in Jazzer, we built bug detectors for remote code execution, SQL injection. So these are the kind of bugs that you would have in a, for example, in a Java application that you normally use, for example, to develop backend or an API. How does fuzz testing differ from static analysis in identifying memory corruption bugs? Is it faster? Um, so the main difference is that fuzz testing is a dynamic analysis. So we actually execute the program that, or the software that we are testing, and then each time feeding it with different inputs, some unexpected inputs, to step by step optimize the code cover and reach as much code as we can. And this has the advantage is that for each bug or issue that CI Fuzz reports, you get a proof of vulnerability, or you get a reproducer. In a sense, you get a concrete test case that if you execute this function or this API with this test case, you will trigger this vulnerability. And you get also the detailed stack trace containing the chain of function code leads to this vulnerability. So you get no false positives, and this is the main advantage of fuzz testing. Static analysis, there you scan through the code, you have to do some approximations. You don't have the actual condition runtime conditions. So this is one of the fundamental changes of fundamental limitations of static analysis, that you cannot prove that the vulnerability is there, and it's the responsibility on your side to actually assess if it's a bug or false positive. And from experience, you get quite a lot of false positives. So while it's maybe faster to scan through the code and just get the finding, you need to spend much more time into trying to assess them and just figuring out the false positives, which would be quite a lot. Do you recommend companies conduct fuzz testing locally at the dev level, or should they be run in a CI pipeline? This is actually a very good question. So fuzz testing is most effective when it's continuously applied. So it's instead of just running it sometime on your local machine, it's most effective when it's done continuously. And this is why it's ideally it's integrated into your CI/CD pipeline, so that any code change that introduces a bug similar to the one that we saw with the Heartbleed vulnerability, CI, so fuzz testing will be then able to hopefully quickly trigger this bug, and so that maybe your pull request would fail until you fix this bug, so that these bugs don't end up in production. So on the question, the difference between fuzzing from code intelligence compared to other dynamic testing tools. So what we do at Code Intelligence is basically mainly whitebox fuzz testing, meaning that we leverage the source code, the source code insights into so we leverage instrumentation to maximize code coverage, and we use a lot of under the hoods also open source fuzzing engines like libfuzzer and EFL++. But this addresses the sort of the running and executing the test part, so this step that there. So we rely on that, but for running and executing the fuzz test, we so have a lot of convenience features. For example, in this, as we said in the demo, all I had to do was CI Fuzz run without having to manually specify the concrete flags that you need to use. So we take care of that, so that you don't have to be aware of those. Coverage, so idea reporting and CI/CD integration. So this is something that you don't normally have with open source tools off the box. But currently, our main focus was on making it as accessible, as automated as possible, with the what we call candidate selection and automated fast test generation, so that, and this is not something that you have with open source. So this is the main focus right now, and also soon we will have we'll show so the second degree, the next degree of automation that you can do, where you can combine all these building blocks into a fully automated solution. This is will come soon as well. Can fuzz testing analyze binaries? Yes, it can. There are even techniques to, like, even because, as we talked about, in order to do it to have this coverage information, you need to instrument the code. So ideally, you have the source code so that you can do this instrumentation at compile time. But even if you do not have the source code, there are sort of binary instrumentation techniques that you can leverage in order to get some feedback information about the coverage that you reach. These are less effective than if you have the source code, but it's possible. So far, from as a user, most of them, they are interested in testing their own code, but not third-party code. But it's possible. Another question: lots of developers' time is consumed in writing tests. Huge blocker. Can it help to replace unit tests? So there are tools or other tools that helps create or automate the creation of unit tests. This is not a focus for us right now, but we leverage unit tests. If there are existing unit tests, we leverage those in generating high quality fast tests. Okay, I think we don't have more questions. Can we 2 seconds just if there are more questions? Yeah, if there are no more questions, thanks everyone for your attention, for the great questions, and join us in October for the AutoSAR simulator or testing automated software in a manual loop, and also with our upcoming webinars where we discuss the automation that we are building into CI Fuzz. So thanks a lot and have a great evening, everyone.